Awesome. So this is a talk about a paper with Dave. It just got accepted. It's forthcoming in Synthèse. And actually, before I get started, I just want to say thanks to the organizers of the workshop. This is really great. It's really nice to be able to see everyone again. It's been a long time since all the COVID disruptions, and also to have a bunch of people that I don't know but are watching, and hopefully I'll get to meet at some point. So this is really a good opportunity for all of us. I'm really thankful for that. Okay, so let me just get started. I'm just going to try to set up a bit of the context for my talk, and I think Flavio went through this. I wasn't there because I had to teach, but I've seen his slides, so I know what he should have said. But I'll just go over a little quickly history of, very quickly, too quickly, of how shapes develops to set up the context. So I think a lot of it started in the 70s with York. Julian mentioned this yesterday, who came up with a way of finding an initial data set for GR, at least for a pretty good class of solutions to GR, in terms of conformal 3 geometry, and one global degree of freedom, which is the 3 volume, plus the velocity. So the idea is you find an initial set of data that solves all of the constraints of GR, and it winds up that you can choose the lapse. You can choose a choice of foliation, such that the degrees of freedom are invariant under local scale transformations, except you still have this global volume, which you need to keep. And so then, skip ahead about 33 years. And then we have this important paper by these people, Anderson, Barber, Foster, Keller, and Morhew. And they were, I think, well, this is really the first concrete shape dynamics proposal, in the sense that they were using York's results. And they were proposing that we take these conformal degrees of freedom seriously. So it was a kind of shift of ontology. It was really a new theory. It's a new way of thinking about general relativity. So forget about space-time, the space-time derivation of general relativity, and focus on this conformal decomposition. Say maybe this is really what's happening, because the conformal geometry, the shapes are what we really measure. And so that paper got Tim and myself and Enrique really interested. Julian gave a talk, I think in 2007 at Perimeter, and we were like, man, if Julian's right about this, then it's super interesting. But there were some things we wanted to understand. This paper was, the theory was expressed in a particular gauge, so in a particular conformal section, you can do this decomposition. We wanted to show that you could do it in any conformal section, so that you could take these conformal degrees of freedom and look at them in any conformal gauge. So another way of saying that is that what we were able to show was that there is a theory, a gauge theory, that's invariant under local scale transformations, and it lives on the same phase space as general relativity, and it's equivalent in the precise sense that there's a larger theory, which is called the linking theory, for which general relativity is a gauge fixing and shape dynamics is a gauge fixing. So what we did in the paper, or actually I think it might have been, we did this in the paper, but we didn't have the language. Tim and Enrique filled out the details a bit later. Idea was you start with a bigger theory with more variables, and then you can do one gauge fixing, you get general relativity, you get a different one, you get shape dynamic, or this theory which we were calling shape dynamics. But the important thing, so the story at that time was that there is a theory which is locally but not globally equivalent to general relativity, and this is local in space-time, I suppose. So there were solutions of general relativity that were not solutions of this theory, because these gauge fixings are not always available. and possibly vice versa. So that was what was interesting, is that can we really explore this theory? Now, the main thing that, so we wrote lots of papers, and there's still lots of work to do. But one of the big mysteries was that we couldn't trade the global scale. So we couldn't get rid of this global volume that was sitting in the York decomposition. And it was just not clear what to do with that. So that's why I call this the first shapes revolution, just stealing from strings, or SD1. I think it's a good language to use to distinguish different concepts, because a lot of the talks yesterday were not really about that. They were more about what I would call the second shapes revolution, which is how an exciting way of trying to get rid of the global scale as well. But the mechanism is very different. This is not about symmetry trading. This is not about looking for a surface of simultaneity in which the degrees are conformal. This is really a different idea. And it was proposed first by Julian Barber and Neil Morhew in this paper in 2010. At least that's, I remember them talking about this. And they proposed that a symmetry called dynamical similarity could be used to get rid of the global scale. And I'll talk more about that later. I think Fabio might have mentioned it, possibly Julian as well. Now, another thing that's worth mentioning is that independently of all these arguments, Ashtekar and Sloan, so Dave and his supervisor at the time, I guess he was a supervisor at the time, maybe not, they argued independently that dynamical similarity should be thought of as a gauge theory in cosmology. So they had that same argument using different principles. And eventually Dave came together with us and we started thinking about this. Now, what's the fallout of this? So I said there's still lots of really interesting questions in SD1, even before thinking about this. And to be honest, it's not that the questions stopped being interesting, it's mostly that many of us had to get paid to keep doing this, and we had to either drift to philosophy or do other things. So there's still lots of really interesting work to be done. The role of the CMC gauge, description of black holes, quantum mechanics, all kinds of interesting questions. But this workshop is mostly focused, I've noticed, on the consequences of dynamical similarity. And I'll talk more about why I think that's the case. Now, this is a comment I want to make, and this is also to the shape dynamics people, that SD2 is really fundamentally different character kind of theory than general relativity. And I'll try to explain what I mean by that. Even though you can reconstruct all the GR solutions, there's something really different about how the theory is used, and how inferences are made, and how which is why you'll see this is why you get into these ability to answer questions about things like the arrow of time. Anyway, so my talk is going to you can see it as a shapes independent philosophical exploration of SD2. So let me just recap what the shapey argument tends to be. And I don't know, I just like reading this quote. It's Poincaré. I think he highlights some of the intuition that I often have when I talk about shape dynamics. So he says in Science and Method, 1908, suppose that in one night all the dimensions of the universe became 1,000 times larger. The world would remain similar to itself if we give the word similitude the meaning it has in the third book of Euclid. So this is where the similarity from dynamical similarity comes from. Only what was formerly a meter long will now measure a kilometer. What was a millimeter will now be a meter. The bed in which I went to sleep and my body itself will have grown in the same proportion. When I wake in the morning, what will be my feeling in face of such an astonishing transformation? Well, I shall not notice anything at all. The most exact measures will be incapable of revealing anything of this tremendous change, since the yard measures I shall use will have varied in exact same proportions as the objects I shall attempt to measure. Okay, so why did I read that? Because it's supposed to be, so this intuition is captured by the obvious fact that the absolute spatial size of the universe is not empirically accessible. So what Poincaré is saying is, if I were to blow up the world, I'm also blowing up all the rods that I use to measure distances. And since measurements of distances are relative, if I scale everything together, there's no observable difference. Okay, that's often more or less how I start my talks in shape dynamics. And I put obvious in quotations because I've found that it's not obvious to everyone. And I put fact in quotation marks just because I now work in an epistemology group, and so I have to put fact. I realize that facts don't mean the same thing to everyone either. But anyway, okay. But I'm getting to a particular point. I'm trying to make a little point here. So let me just, this is supposed to be an obvious fact. I don't know what's happening. Okay, it's supposed to be an obvious fact, but well, it has some pretty interesting non-obvious implications. So if this is true, it means the scale factor of the universe is unobservable. Why? Because scale factor A, which is the thing that appears in that multiplies the spatial distances, is the thing that Poincaré is saying you want to change, and that rescales all the matter, all the things you're trying to measure, and the rods themselves. So all that gets rescaled under this transformation. So what does it mean for the universe to expand? And Julian has often said, like, that universal expansion is some kind of a lie, or I don't know what it is, illusion. What do we directly measure? We measure things like redshift. So redshifts are ratios of lengths. They're looking at how the wavelength of light, which comes to us from distant stars, compares with the wavelength of light created in similar conditions in the lab. We could just compare those, and they're different. And that's the redshift. That would mean that the scale factor is some kind of gauge variable, but the redshift is not. The redshift is observable. Now, what's interesting is that if you do the short canonical analysis, you find that, well, the V, so a to the 3 halves power, is just canonically conjugate to h. So it would mean that something that's a gauge variable is canonically conjugate to something that's observable. It's a very different, if this is a gauge symmetry, if changing A is really a gauge symmetry, it has to be a very different kind of gauge symmetry than the gauge symmetries that we're used to, because the gauge symmetries of general relativity and electromagnetism and all the standard model symmetries are all symmetries that preserve the symplectic structure. The things that are canonically conjugate are still canonically conjugate to each other after doing the gauge transformation. That's not the case. That would not be the case here. So, so that's why it has these radical friction-like implications. And I'll get into that in a bit. Okay. So, but things like unobservable and directly measurable, we've known for, from the philosophy of science literature the past 70 years that these words are theory laden, that what is observable and unobservable and how we measure things. There's a lot of theory that goes into that. How do you measure ratios? How do you measure redshifts? There's a huge amount of all kinds of different theory. And just saying by fiat that shapes or angles are what we measure is a metaphysically strong assumption. To say that shapes are real is quite metaphysically strong. Now, I'm not saying that's a problem. In science, it's perfectly valid methodology to make strong ontological assumptions, carry them through to the end, and see if you get somewhere with it. But it would also be nice, it's a kind of vindication of that methodology if you can find a way to do it without those assumptions and stick to more empiricist-like intuitions. So let me try to consider just a more neutral approach. So let me just look at the formal properties of an action. It can be anything, and consider a transformation between solutions. So these solutions, gamma to gamma prime, this is a transformation that sends some curve to some other curves. This is meant to represent the history. It's the thing that you plug into the action. Okay, and I want to, and this transformation is such that the action gets rescaled. So what you're doing is you're going from one curve to another curve in such a way that the unit of action, which is either an angular momentum or an energy times time, however you want to think about it, gets rescaled. Now this symmetry, this transformation is a symmetry because it preserves the stationarity condition. You can see that, right? If gamma is a classical solution, gamma prime will also be a classical solution. And that's a fairly common definition of a symmetry. The question is, what kind of symmetry is it? So almost every theory, if you have a transformation like this, will have symmetry of this kind. The question is it a physical symmetry? Does it relate physically distinguishable solutions? Or does it relate physically indistinguishable ones? And how can you tell the difference? Because sometimes, as we'll see, the dynamical similarities in the Kepler problem, for example, are physical symmetries. They do relate physically distinguishable solutions, but sometimes they don't. At least that's what we're claiming. We will claim that we want to say that in cosmology, they're relating indistinguishable solutions. So how can you tell the difference? And that's why we developed this framework. Okay, so how are we going to do that? Well, I'll introduce in a bit more detail dynamical similarity. Then I'll talk about the principle, and then I'll show how it works with some examples. If I have time, I hope I'll have time to talk about the arrow of time in a bit more detail. Okay. So what time is it? Okay. So let me just, I just talked very briefly about about what these transformations look like. Let me get into a little bit more nuts and bolts, but not too much more nuts and bolts, because Dave is going to do this much better after me. So stay tuned for that. You can write a general action this way, q dot p minus h, and just think of a transformation that rescales the position and the momenta in a different way, so that the product q times p gets rescaled by c. Okay. Then, as long as you rescale time, so under this transformation, the Hamiltonian will have some kind of transformation property. Okay, there's some caveat here, but don't worry too much about it. Then if t rescales this way, then the whole action, so this term and this term, gets rescaled by c. Okay. So these are the kinds of transformations we're talking about. They act on the phase space in this sort of way, such that q times p gets rescaled, and they reparameterize. It depends a little bit what b is. Maybe you can pick b. Maybe b happens to be something that, because b will depend on the form of the Hamiltonian. So if you're lucky, maybe you can get c over b to be 1. That happens in cosmology, actually. But in general, you'll get a reparameterized solution. Okay, this is what we are calling a dynamical similarity. Now, I just said that it acts on phase space crossed with time. So what space is that? This is, if I just draw a little picture here, this is phase space, and this is time. And you get a curve as a embedding, right? So you just map, a curve is just a map from this time to phase space, okay? Now, along any curve, there will be a group action. You can see that because just acting like scalar multiplication on Q and P, up to a reparameterization, okay? So up to a reparameterization, this symmetry along a particular curve will have some group action. Now, I'm just going to tell you this, it's true, that, but you have to check it. it's not that hard, that if the curve is classical, it also has a group action period. So you might worry that when I reparameterize this curve, that I won't be able to get to the new curve by following an arrow. But it turns out that if this is a classical curve, there is a vector field that will take me to the new reparameterized curve. Okay, and that's just to justify this picture. It means that I can think of the phase space. These classical curves will foliate the phase space, at least locally. So what it means is that I can think of the phase space as having these orbits that I get to by following these vectors. So each curve will have another arrow, and I can follow that and kind of trace out the orbit. So all of the points that are on the orbit are like points that are equivalent under a dynamical similarity. So this is starting to look a lot like a kind of conventional fiber bundle, except it's as if the fibers are directions in phase space. And the base space is some kind of, phase space minus one dimension, which is not a phase space itself. Okay, so that's part of the problem, is that normally if you have a gauge theory, you get these orbits and you want to just quotient by the actions. You want to take maybe one representative of each of these curves and project onto one of those, that representative. That's what a gauge fixing would be. The problem is that, well, it's not a problem. What's different about this is that this is not a fiber bundle over space-time or something. It's not even a fiber bundle over configuration space. It's a fiber bundle over space-time, phase space. And the way that we define D, it rescales the symplectic form. Remember, P and Q got rescaled in such a way that they got a C in front of them. So what that means is that this vector field is not preserving the symplectic 2 form of the theory. It's not going to preserve the Poisson bracket on this phase space. And in particular, it's not going to preserve the Liouville measure. Because this thing gets rescaled, and so all these C's will come out, C to the N will come out of this. Okay, that's significant, because normally you think of the Liouville measure as something that's preserved by the dynamics. But if we want to project out the effects of dynamical similarity, then we're going to find that the Liouville measure is not preserved anymore. Okay, so that's what I just said. Think about the picture here. So suppose we just want to do it as a mathematical exercise. How do we quotient by dynamical similarity? Well, we would do exactly what I said, pick a representative. So you find some surface that's normal to the flow of this vector field. And then you break it up, you take the flow of the Hamiltonian. Okay, so that's the tangent to this curve, classical curve that we have. And you break it up into components. The component that's perpendicular to the surface and the component that's parallel to the surface. Okay, that's great. But you notice that the perpendicular component is the component of the Hamiltonian along this vector field D. And so this vector field V perpendicular is not going to be also not going to preserve the symplectic form. So V perp, so even though VH is conserving the Liouville measure, V perp is not. Sorry, V perp is not, but V parallel is not. This is the projected flow, the dynamically similar flow, let's say. Now, Dave is going to talk a lot more about this. He'll probably do it a slightly different way. He'll give you the explicit form of these equations, which are interesting. But this is the picture. Okay. All right, great. So I just tried to argue for you, although I didn't show you any of the equations, just using basic principles. You should expect that the Liouville measure will evolve. Now, these things happen to look like friction or anti-friction terms. Flavio already talked about that in his talk. Now, Julian and Flavio, like I said, already mentioned this, that there are many systems, many interesting systems like cosmology, Bianchi models, and body problems, where the volume, the Liouville measure, shrinks and grows around these, what Julian calls Janus points. But also, what Flavio was showing too was that the volume shrinks to 0 near these attractors. I'll talk about this. I hope I have time to talk about this a bit later. Now, the last thing that can happen is that V perp could be the only non-integral part of the flow of V. So if you have this is the, say, the Hamiltonian flow in general relativity, it could be that the perpendicular flow is the only part that's non-integrable, and this part still is. And that's sort of one way to understand what the singularity resolution that Flavio was talking about in his talk. Okay, now what's interesting is that measures affect all kinds of calculations, even in classical theory. So when you're talking about how the behavior of collections of solutions, you're talking about counting possibility. And what are the things that you think are likely to happen in the theory that you're talking about? So if you have a symmetry that dramatically changes the way that the measures behave, then so many of the inferences that you make in a theory are going to be affected. So whatever priors you have about what is likely, whatever typicality measures you want to use, statistical inferences, so credences. The point is that even in classical theory, we use evidence to build our credences for certain theories. So even though we're always just talking about a single, we only believe in classical theory that only one of these solutions is actualized, the way we conceptualize about a theory is by imagining all the possible things that could happen. And that is dramatically different when you change the measures. So that is why I think, this is also the point I want to make to the shape dynamics. This is why this effect of quotienting by dynamical similarity can have such a profound effect on the way we conceptualize about the theory. Okay, so yeah, I talked about a little bit about this. The question is, are we justified in doing this projection? So I hope I was able to convince you that if we do this projection, it really radically alters the theory. Are we allowed to do it? Are we justified in doing it? Now, interestingly, dynamical similarity fits the kind of textbook definition of a gauge symmetry. If you look in Hanon's textbook, so Hanon and Tiedeborn, for example, they define this as a gauge symmetry. Yeah, so that's great. And there are really strong norms for quotienting by gauge symmetries. The problem is that there's lots of formal ways in which dynamical similarities are different from conventional gauge symmetries. For example, there's no Noether's second theorem for a dynamical similarity, because for that you need this term to be 0. There's no initial value constraints like the Gauss constraint, electromagnetism. There's no degeneracy in the equations of motion. The equations of motion are completely determined even before you take out dynamical similarity. That's not the case for standard gauge symmetry. What's underdetermined is the variational principle. The action can't tell you the difference between all the different solutions that are related by dynamical similarity, but the equations of motion are still well posed for each of those solutions. So I just made a comment that even though that may seem like a really dramatic difference, all of what I said is also true for Leibniz shifts. If I move the universe a meter to the left, that transformation will still satisfy this property. But there's no other second theorem for that. There's no initial value constraint. There's no degeneracy. So it's not completely crazy to think this could still be a gauge symmetry. Okay, I actually said all this already, so I think I should have just taken the slide out. Now I'm going to talk about the principle I want to use. it's inspired by two things. One is it's very close philosophically to a proposal by Adam Colton from 2015. So what I'm doing is I'm coming up with a proposal for how to tell whether a symmetry should be treated as gauge or not. Okay, and Colton said, well, what you should do is maximize all the analytic symmetries as long as you can still preserve empirical content. So you make the gauge symmetries bigger and bigger until you've stripped the theory's ability to describe the empirical phenomenon. That sounds like a really nice principle to me. The issue I have with it, or the problem I have using it in practice, is that there's no dynamical criteria. He explicitly doesn't give a dynamical criteria for what analytic, or what he calls an analytic symmetry is very close to what physicists would just call a gauge symmetry. The differences are, whatever differences may or may not exist, are not that important for my talk. But anyway, okay, so you could use something like this, but he doesn't. And I think the reason why he doesn't want to do that is because 2 years before this, Gordon Bello wrote a paper where he gave a whole bunch of different criteria and kind of tried to argue that none of them work very well. So if you want to do this, you have to find something that was not in Bello's paper. But until you know what, just declaring by fiat that a symmetry is analytic is not really enough. You really have to know what it means formally if you want to use this theory to add or remove a symmetry. So then we go to the physics literature. And, it's interesting that Gordon's intuition seems to be completely different from physicists' intuition. This is a quote from Hanot and Tiedeborn. They just say, the action itself enables one to decide what are the observables. So what they're trying to say is, from the action, you can tell what the observables of the theory are, period. And if you know what the observables are, then you can know what symmetries are, the gauge symmetries. How do they do that? So they propose to do that using a proposal by Dirac, which is you start with the algebra of all phase space functions. So this is already now restricting to theories that can be described on phase space. And then, so in electromagnetism, this could just be the electromagnetic potential and the electric field, okay? Then you look at the first class constraints, all right? It doesn't really matter what these are. An example is the Gauss constraint. But you can get these from the action. Then you look at the smaller set of algebra A, which the elements of which all Poisson commute with these constraints. That's the proposal. So it says the observables you get because the Poisson bracket from the Legendre transform, the canonical constraints from the action. So you get all of this just from the action. And those observables are supposed to represent the physically distinct structures. I'm pretty sure that's almost the exact word that Dirac uses. So you have this very clear formal criteria, a way of getting from the action to the observables. But it's not something that's going to work for us because, the great thing is that he's able to be very specific. The bad thing is that has to assume lots of structure. He has to assume that the symmetry preserves the Poisson bracket, but the Poisson bracket is still well defined after you apply the symmetry. He has to assume that there are initial value constraints. There are no initial value constraints for dynamical similarity. So this is not going to work for us. We need a different way. But the nice thing is we could just sort of generalize Dirac's methodology a little bit. So what is his methodology? Well, he said, take a dynamical system that's not well posed, that lives on this larger phase space, and just find a smaller algebra in terms of which the projection from that original system to the smaller system is well posed. And then you just hypothesize that those, the elements of those smaller algebra are the things you want to use to describe the phenomena. So these things are going to be isomorphic to measurement reports. So things like that you write in the lab book. Okay. And then you can go out and test whether this hypothesis is correct. The idea of the Pisa, I skipped through the name of this thing. The principle of essential and sufficient autonomy is what it's supposed to be. Sorry, I skipped through that. Anyway, the Pisa, let's call it, is to follow this philosophy, but not to worry about the kind of dynamical system that you have. So you just look for the minimal, well-posed, empirically adequate dynamical system. And once you have that, you can use that to figure out what the gauge symmetries are. In some sense, the independent initial data form a generating set for the algebra of the observables. So once you find the system, you use that to construct the observables, and we call these Poincaré observables because this is the kind of thing that Poincaré suggested in some of his early papers. Yeah, you have to trust me on that one. It's in our paper if you want to know a bit more about that. What is it specifically? What is the Pisa specifically? So consider a dynamical system. This is following the same logic. You think about some algebra. It could be phase-based functions. It could be anything else. So the elements, the dynamical equations of the system will be first-order equations in terms of the elements of this algebra. And if you're worried that this is not going to be general enough to include a second-order system, then just redefine your variables, call V double dot V dot, and then you can redefine it into a first-order system. Okay, so this is still very general. It doesn't matter. These equations don't have to be well posed, and in general, they won't be. What you do want to be well posed will be its projection onto this smaller space. So a smaller algebra that sits inside B, and a generating set of it should obey some kind of equation like this. So this is just the projection of these equations onto this subalgebra. Okay, then you consider, all right, hopefully you're following. So this is like the phase-based functions. These are like the Dirac observables. Now you say, just consider the space of hypothesized measure. So it's, what do you think you're going to be able to describe for this theory? The space of all possible measurement reports that you think the theory is going to be able to describe. Okay? You don't know, this is not the space of all possible things. It's just a hypothesis about what you think the theory is going to be able to measure. And then you consider the map of, this map O from A to P. Okay, consider a map from this space A to the space of hypothesized measurement reports. Okay, so the principle is equation 4, sorry, I couldn't, if equation 4 is autonomous in A, that means it could be written in a way that doesn't depend on T, it only depends on A. If this map is onto, so if this algebra has sufficient structure to represent the phenomena, if it's one-to-one, so if it has the necessary structure to represent the phenomena, and if the theory is empirically adequate, then you can say that the observables live in A. And we call those the Poincaré observables. So this is a bit formal. I don't know how straightforward it is to follow this. But the bottom line is you just look for the minimal algebra that's necessary. I think I say it in the next slide. Okay, you quotient formally by as many symmetries as possible. So you project down to lower and lower spaces until you can no longer autonomously represent the target system. That's sort of like a more precise version of implementation of Colton's idea. This is make sure that you count everything. So this is not just like particle positions and other things, but there could also be particle masses, coupling constants. Make sure you count everything in that. And then you focus on the smallest empirically adequate, well-posed system. That's the inspiration that we have from Dirac. Okay, so like I said, that's the proposal. It's just based on formal criteria of the different properties of the equations of motion and this requirement of empirical adequacy. We don't have to assume any metaphysics in the principle, and it tells you what the observables are. Okay, so I'm running short of time, but let me talk about, I think I started, what time did I start?
I think you have 10 more minutes, if that's okay, or 5
Yeah,
more
okay.
minutes.
Okay. I can go through these examples relatively quickly, I think. Let's see the principle in action. I wanted to focus on that, but let's see it in action. So Kepler. Okay, the Kepler is a 1 over r squared r potential. So the action looks something like this. This is the angle of the Kepler's particle moving around an orbit. Okay, this transformation is a dynamical similarity. If I rescale r and I rescale t in this way, then the Lagrangian gets rescaled. And that's what we call the dynamical similarity. Now, Gordon Bello and David Wallace talk about these wrong lens symmetries. And they use them as examples against being able to talk about when they're trying to, sorry, Gordon uses this as a way to show that there's no good dynamical criteria for a gauge symmetry. But what he doesn't say is that these are just dynamical similarities, actually. I think he describes them as some non-intuitive transformation of the momenta or something that are not very enlightening. But actually, that's it's not true. It's not true that it's not the transformations are not enlightened. They're dynamical similarities. So it's related to Kepler's third. It's consistent with Kepler's third law. In Kepler's third law, the square of the period is related to the cube of the semi-major axis. But what's cool about that is that this quantity is just an invariant under dynamical similarity. So you expect that there are solutions that are related by this because dynamical similarity is a symmetry of the Kepler problem. So it doesn't get you all of Kepler's law, but it gets you Kepler's third law, but it gets you some of it. Now, okay, what is a generating set for the velocity phase space of the Kepler problem? Well, you have R. If you look at the Lagrangian of R, you have R dot, you have theta dot. So you have R dot, theta, and theta dot. Now, you can write a generating set for the invariance of dynamical similarity just by taking factors of root R and dividing. So anything that scales by the dynamical similarity, the T and the R, you can use, and you can divide out by the appropriate factor to cancel. So here, there's a T, 1 over T, and the R to the 3/2 can cancel. So this is an invariant. This is an invariant. Theta was always an invariant. But square root of R is not. It's the one that we use to do the canceling. So, so we have, from this algebra, we have a subalgebra that is smaller. The question is, can we describe the Kepler problem without square root of R? And the answer is no. Different Kepler orbits, the Kepler orbits with different scales, so different value of the semi-major axis, are physically distinguishable. If I make the orbit bigger, I have a different Kepler orbit. And the reason is simple physically, just because there are external clocks and rods in the system that can tell you. So you have the Earth itself is a fixed planet. So if you're comparing the orbit of Jupiter to the orbit of Saturn, you can use the size of the Earth to tell which one is bigger. Here, the algebra A is not sufficient for an empirically adequate theory. So you shouldn't quotient by dynamical similarity. The Poincaré observables for the system are B. B is sufficient and necessary for being able to describe the Kepler problem, and not A. So you don't quotient by dynamical similarity. Now, cosmology is different. So in cosmology, this is the Hamiltonian for FLRW in a proper time gauge. So this is the time here is proper time. And it turns out this is a dynamical similarity. I just rescale V and I rescale the momentum conjugate to the scalar field. And if you look here, you can see why. I just have to scale V in the same way as P phi, and I'll get an invariant. And then the rest of it, this is okay, so the rest of the invariants are H and V. And you can see that here, all this is consistent. The idea is that proper time, this is one of those cases where the time doesn't get rescaled under dynamical similarity. So, so then the redshift is just going to be invariant because it's V dot divided by V. Time is invariant, and V just gets rescaled. The velocity of the scalar field is also an invariant. I can take PV divided by V, I get an invariant, and the scalar fields are all invariant themselves. So now the cool thing is that the equations of motion are the Friedmann equations, but these are autonomous in the invariance of dynamical similarity, or at least they can be written autonomously. I can get rid of the T dependence here just by using one of these fields as a clock. So the important thing is that these equations only involve these things. They don't involve V, which was the thing, or P phi. So the generating set for the phase space of cosmology, FLRW cosmology, it has a V, it has a redshift, it has these things. The dynamically similar invariants, the DS invariants are one smaller because the V has been removed. Some power of V is just the scale factor. Okay, but the Friedmann equations are necessary and sufficient for empirical adequacy, at least for the background equations of cosmology. So the point is that I can get an empirically adequate theory just by having an autonomous set of a set of equations that are autonomous in this smaller algebra, capital A. So the PISA tells me that A is the generating set for the Poincaré observables and not B. So here, the PISA is telling us that we should quotient by dynamical similarity and that the scale factor is gauge. Just saying that we got here just through these formal and empirical requirements. We didn't need any shape the argument. We didn't need to leverage the quote by Poincaré or assume that angles are real. I have a hand up.
Yeah.
I don't know. I actually don't know who it is because I can't see it on here.
Yeah, Sahant has his hand.
Should I take questions at the end or? Huh?
Yeah,
Pardon?
if you wish, but my suggestion would be that you finish first and then we go into the discussion.
Okay.
But as you.
So I'm not sure exactly how much time I have to talk about the arrow of time.
Is 5 minutes okay? So we have.
Yeah, no, 5 minutes is more than enough. Yeah. I want to have some time for discussion. Okay, so let's see. I said this already, so I can go through this quickly. I just want to remind you that we have this projected flow. So when you quotient by dynamical similarity, you get these terms that are not conservative. They're not preserving the, they're frictional because they're along D and D is not symplectic. Okay, so the Liouville measure we expect to evolve in cosmology, or in general when we quotient by dynamical similarity. So if you have a evolving Liouville measure, then you could look at some interesting points of the dynamics of the Liouville measure. So for example, if there is a region of phase space where the Liouville measure changes sign, we're going to call that a Janus surface, the region R as a Janus surface. So there are two ways that mu dot can change sign. It can go through 0. That's the obvious way. We call that a type 1 Janus surface. This is the kind of thing you get in the n-body problem. But there's also a type 2 Janus surface where mu L goes from minus infinity to plus infinity as it moves through R. Whoops, this should be R plus, sorry. And this is the kind of Janus surface that you have in the Bianchi models and the FLRW cosmology. So it's actually pretty important to note that the kind of Janus point that you have in cosmology is really significant, substantive. It's quantitatively and qualitatively very different from the kind of Janus surface you have in the n-body problem. So there are significant ways in which the n-body collision is different from the Big Bang. And that's captured by this difference between type 1 and type 2. But what is the same is that the flow of the system is momentarily conservative. The friction terms become unimportant at this point. I have to say it that way because the friction terms are infinite, but they're a smaller infinity than the rest of the energy of the degrees of freedom. So anyway, that's what's the same, that the system is momentarily friction free. At least the friction is not important, let's say. Okay, so an attractor, let me just give you the formal definition, is if you have the flow from a region B, which is the attractive basin, converges in some time to a point, it's called an attractor. Let me just show you the picture. So if I have a region B and all the trajectories go in a large T limit to some other region, it could be a point, then that region is called an attractor. So what happens if we have a Janus surface that lives in the attractive basin of the attractor of some theory? Now this attractor only really exists because the Liouville measure is evolving, and so as you go along the flow flow is scrunching up. Now if this happens, there's the proposal that there's a natural arrow of time that points from the Janus surface to the attractor. Why do I say that's a natural arrow of time? Because if I were to look at the Liouville measure on some region here and follow that region to a similar region here, so the same solutions, I look at the same solutions as they move along, and I look at how the Liouville measure evolves along that region, then it shrinks dramatically as you get to the attractor. That's what happens. And I talk about this O as being an epistemically thick observer. The point is that if you're a reasonable observer in a universe like this, you can't always tell the difference between the different solutions. You have some uncertainty in your measurements. So for all you can tell, all of the solutions in this thing that I drew are the same. I can't distinguish epistemically between these different solutions. But if I trace that back over here, then I get a huge spread of solutions, with very large Liouville volume. And it's that asymmetry, the asymmetry of this counting of the Liouville measure that I claim is leading to a temporal asymmetry here. So in some sense, the closeness to the attractor is creating this asymmetry in the Liouville measure and the evolution of the Liouville measure. Let me put it a different way. Oh yeah, so the cool thing about this arrow of time is that it's a property of the global structure of the solution space, so the existence of Janus points and attractors. But it really is something that only a special class of observers sees. The observers that are near the attractor will see the arrow of time. And the same observer here would not see this asymmetry in the measure. And so they won't see any definite arrow of time if they're close here. But if they're, as they get closer to the attractor, they see a stronger arrow of time. Okay, well, it turns out that, is this enough to explain the time asymmetry in the universe? Well, we have 85 orders of magnitude. So that should be enough to explain a huge amount of time asymmetry. Just the point is that when you start changing the way that measures behave in the theory, it really dramatically affects the kinds of inferences that you make with the theory. And that's what happens when you quotient by dynamical similarity. Thanks.
Thank you very much. Well, again, a very inspiring and thought-provoking talk. And we already had 2 questions. Enrique was first.
Hi, Sean. Thanks
for
that. Sorry, I came in a little bit late. I don't know if you addressed these questions in the beginning. So usually the problems with indeterminacy of the solutions and so on, they come from time-dependent symmetries or a Hessian, which is degenerate. So if you can have a symmetry of the action that doesn't really matter for determinism, as you say, because the initial value problems determine, initial value data determines the data throughout. And it's you know, translation and so on. Well, depends on your system. But it, and so that's one question that I had, if it's time dependent. And the other question is that I think the empirical observability of a symmetry, which is something, or the observability of a symmetry transformation, which is something that is in the background here, is to recall a theme from the chat yesterday, a property of subsystems. And then, you know, if you have the Lenz-Runge, I don't know how you pronounce that, to be honest, but the Lenz-Runge symmetry, if you include other things like planets going through the Kepler pair and so on, it would no longer be a symmetry. So there's this matter of observability of a symmetry. I think it's inextricable from how you couple subsystems and whether symmetries of subsystems are extendable to environment or to the other subsystems. This is a theme from David Wallace's recent trio of paper, and also my own papers. And so I'm wondering first if DS is a symmetry that can be applied to subsystems, whether it has a unique extendability to the rest of the system, and whether it is a time-dependent symmetry or not.
Great. All right. So I can answer both of those questions. Actually, the answers, we go through this in detail in our paper. So actually, I didn't do it in the talk, but it's obviously, I use the PISA. So we spent a lot more time going through the PISA in the paper and applying it to different examples. And the Galileo ship is one of them that we do on top of dynamical similarity. Now, what we do in the paper is we distinguish between universal symmetry and a subsystem symmetry. And the way we discern between those is a universal symmetry is one that leaves all the Poincare observables invariant, whereas a subsystem symmetry only leaves a subset of them invariant. And so that's one way to distinguish. And yes, you can do that for dynamical similarity. So you can find dynamical similarities that act on the subsystem of the size of the Kepler orbits, but they don't change. So suppose you have one of the examples we looked at in the paper was if you give the Earth a little bit of thickness, so you allow it to have a size, and allow it to rotate about its own axis as it's going around in its Kepler orbit. Then the dynamical similarity can act on the orbit, but it won't. You can have it not act on the size of the Earth, and then it's a subsystem symmetry. And then when you do it that way, you find that it's not. Basically, what we did is we did explicitly what I said. You put in an external clock and rod, and then you can show that that the transformations that are physically discernible in the Kepler problem are transformations that act on a subsystem and not on the full system. If you rescale, if you did a dynamical similarity that also rescaled the size of the Earth, that would be unobservable. I don't know if maybe you should just read the paper. Actually, wait a second, because I have to update the version. It just got accepted, and I haven't had time to do all the up. There were lots of updates to the revisions. So anyway, and it is a time-dependent transformation.
It is, or it isn't. Sorry, I didn't understand what you just said.
No.
It's well, T rescales. So yes, it is. You get a reparameterized curve, but the way that T rescales is a constant change usually.
But I'm asking if you can implement a parameter that is itself time dependent, a parameter of the scale that is time dependent. Can you scale differently at different times?
Let me think about that. Yes. No, you can't. That's if you have a solution, you can rescale to another solution. That rescaling is time. It's not time independent, but it'd be T rescales, right? So you get a new solution, a different time parameter, but it's like that rescaling is the same at all times.
Yeah, so I would say that's time independent. So
you can act once on a history.
Yeah, right. Yeah, right. And I think, Hanoi Tatomboyam, they wouldn't classify that as a gauge symmetry. They would say that it's.
I disagree. I mean, if you look, they just say that it's
because it's just, it has to be the degeneracy of the Hessian to have to.
It is the degeneracy of the Hessian. That's the point.
No.
That's why it's not that. So you have to distinguish between the second functional derivative of S and degeneracies in the symplectic form. Those are not necessarily the same thing. One does not necessarily imply the other. I think what you're thinking about are degeneracies of the symplectic form that you get. That, I agree, is not, there's no degeneracy there for dynamical similarity. But the second functional derivative of the action is 0 for that symmetry. So this is different, but it's just a different definition. And the one that they use in their book is the second one.
Depends on which chapter. In one chapter
exactly.
they use what Enrique is talking about, and one chapter
That's right.
what Sean's talking about. So